Hi guys, today we want to take a look at some of the properties of solids, especially from the perspective of intermolecular forces, or IMFs, okay? So solids we looked at in the last unit as well. So some of the properties of our ionic solids, right? Most of them are soluble in polar solvents, specifically soluble in water. So a simple test for determining if water contains ions is to run electricity through it. All right? So you're going to electrocute yourself if you drop the hairdryer in the bathtub, right? But if you have distilled water, I don't know if you'd be willing to try the hairdryer in the bathtub again. This is an interesting statement that the higher the concentration of ions in a solution, the higher the electrical conductivity. So if you had some sodium carbonate, if you had 1 molar sodium carbonate and you compared it to 1 molar sodium chloride, the 1 molar sodium carbonate would be a better conductor of electricity because there are 2 sodium ions and a carbonate ion compared to just a sodium and a chlorine ion in this case of sodium chloride. If you'll remember, our ionic solids they have very strong Coulombic forces of attraction. It takes a whole lot of energy to break apart those crystal lattices, and so you have to add a lot of heat to get them to melt. They have high melting points. They're very hard, and they don't react. They have low volatility. And you've seen this, that our ionic solids will cleave along planes. And so that's something that we looked at in the last unit. Most molecular solids do not conduct electricity when they're either melted or dissolved in water. Acids can ionize, but we will look at acids in a separate unit later in the semester. But molecular solids, the individual molecules, they have no net charge because the valence electrons are tightly held. So most molecular solids are held together by intermolecular forces that are a lot weaker than ionic or covalent bonds. Covalent network solids are held together by a network of covalent bonds, but we'll look at them later in this lesson. Molecular solids, they have much weaker forces. Much weaker forces lead to higher vapor pressures, which we'll talk about later in this lecture as well. But molecular solids are going to have much lower melting and boiling points than ionic solids. So if you took sugar, which is a molecular solid, and salt, which is an ionic solid, the salt would melt at a much higher temperature than the sugar. Molecular shape plays a role, right, in their physical state. And so we looked at this idea of saturated and unsaturated fats in the last lecture. Saturated fats, you'll remember, are solid at room temperature. And then unsaturated fats have at least one double bond, and that's going to change their geometry to produce like a bent shape. So the food industry loves saturated fats because they are not as easily oxidized as unsaturated fats. So you get basically no food energy from a saturated fat. And so they are not good for the body, but they are quite tasty. So in molecular solids, in a solid, the molecules are going to be held together in a regular pattern by intermolecular forces, and you'll remember that these are not as strong as ionic or covalent bonds, but like ionic compounds, we want to maximize attractions and minimize repulsions. So this results in strong dipole-dipole attractions, and that maintains the overall organization of the structure. Remember, molecular solids if it's a polar compound, they can have dipole interactions, and like everything else, they're going to have London dispersion forces. So a heating curve, let's take a look at this. Basically, as you continue to heat a solid, it will stay then at temperature until all of it has liquefied. So the internal energy of the system is increasing, but the temperature is not in these spots because the energy is being used to break the intermolecular forces. So we're breaking the intermolecular forces at phase change. And that's an important point to make if you're answering an FRQ. And so looking at the heat of fusion, we are going from a solid to a liquid. The heat of vaporization, we are going from a liquid to a gas. So heat of fusion is defined as the heat absorbed as 1 mole of a solid liquefies. You'll remember, what we're trying to do is we're trying to disrupt the intermolecular forces. Now, intermolecular forces of attraction are weaker in the liquid phase than they are in the solid phase. So energy has to be absorbed in order to reduce these strengths. Molar heat of fusion values are always positive because we have to put energy in. It is an endothermic process. Now, the name fusion is kind of weird because it sounds like we're putting something together, but not. The fusion, heat of fusion, is defined as the heat gained or absorbed. The heat absorbed as 1 mole of a solid liquefies. Ionic compounds, ionic bonds are much stronger than intermolecular forces, and so the heat of fusion values for ionic compounds are huge. Sodium chloride melts at 801 degrees Celsius. Magnesium sulfide melts at 2000 degrees Celsius. And it's so much larger than a molecular solid because we have to disrupt those ionic bonds rather than the intermolecular forces. So molecular liquids, in a liquid, the intermolecular forces, right, they're still trying to maximize attractions and minimize repulsions. The same intermolecular forces exist in the liquid and the solid phases, but they are not as strong as in the liquid phase. They are not as strong in the liquid phase as they were in the solid phase. But the intermolecular forces in the liquid phase are going to be much stronger than they are in the gas phase, where it's assumed that they're essentially nothing. And that brings us to the heat of vaporization. Again, we're putting heat into the system, so the heat absorbed as 1 mole of a liquid becomes a gas. In a gas, we generally assume that particles have no intermolecular forces of attraction. But in a liquid, they're still pretty large. And so we're going to have to add heat to the system in order for the molecule to enter the gas phase. So this is why if you are in the water and then you get out, you feel cold when you get out of the water, because the heat that's going to be required to evaporate that water is actually pulled out of your body, and it cools you down. And so that is evaporative cooling. Vapor pressure is kind of an interesting concept. So when molecules leave the surface of a liquid to enter the gas phase, they actually exert a pressure, and the vapor pressure depends on the rate of evaporation per unit area. So the rate of evaporation and the vapor pressure are going to increase as the temperature increases. And so if you have the same substance and you have to predict what will happen at a higher temperature, the rate of evaporation will be higher and the vapor pressure will be higher. When two substances are at the same temperature, and this is a good thing to highlight, the rate of evaporation and the vapor pressure will be higher in the substance that has the weaker intermolecular forces. And hopefully that makes sense, because the weaker the intermolecular force, the easier it is to break, the more of those molecules will be entering into the gas phase. And so if we increase that rate of evaporation, we're going to increase the vapor pressure. Looking at water, water has a pressure of about 23 millimeters of mercury at 25 degrees Celsius. But if we heat that up at 90 degrees Celsius, it actually has a pressure of like 526 torr. But again, key concept here, if we have two substances at the same temperature, whoever has the weaker molecular forces is going to have the higher vapor pressure. Boiling points, a liquid boils when its vapor pressure equals the atmospheric pressure. Evaporation occurs inside the liquid when the vapor pressure equals the atmospheric pressure. And those bubbles that happen when you bring something to a roaring boil, they're actually water vapor. They're not air. Pressure is going to increase with the depth in a liquid. And so the vapor pressure may be slightly higher than the atmospheric pressure when the liquid boils, but if in something super, super deep, but the difference is actually negligible. If you take a look, because a liquid boils when its vapor pressure equals the atmospheric pressure, water is going to boil at a lower temperature at higher elevations. At higher elevations, the air is less dense. There are fewer gas molecules per unit volume, so the atmospheric pressure is lower. So this means that the water will boil at a lower temperature, and it usually takes a little longer to cook certain foods. Cooking is an endothermic chemical reaction, and so if the water is not hot enough to input the necessary energy, it really won't cook no matter how long you boil it. So here come pressure cookers. If any of you have an Instant Pot, this is how an Instant Pot works, because if you cook at a higher pressure, the water will boil at a higher temperature, and your food will actually cook faster, thus your Instant Pot. Different liquids, because the partial pressure of a certain gas is determined by the relative number of the particles that are present. The vapor pressure on the surface of a liquid is going to depend on the strength of its intermolecular forces. And so if there are strong intermolecular forces, it's not going to enter the gas phase as easily. When a system requires more energy, it will require more energy to cause its vapor pressure to equal the atmospheric pressure. And so the boiling temperature will be higher for those substances that have stronger intermolecular forces. So if you take a look at some different liquids, as a general rule, the boiling point is going to rise as the amount of energy required to push those liquids into the gas phase increases. And so you notice our first, the only intermolecular forces we have are London dispersion forces. So what's happening between our argon and our methane and our C6H6 is the molecule is getting bigger. It should make sense then that if intermolecular forces are all the same, it's going to take more energy to get more of the bigger molecule into the gas phase than it would be a smaller one. And so we can see that by comparing the first three heats of vaporization as well as boiling points. Now, bring in water. Notice water has our hydrogen bonds, our dipole-dipole interactions, and significantly the heat of vaporization, the amount of energy required is going to be higher, and the boiling point is going to be higher. So that's kind of connection to make there. Special state of sublimation. There are certain things, mothballs, which is naphthalene, and dry ice are probably the biggest examples of sublimation. And so solids can actually evaporate and have a vapor pressure. So these solids that can do this, solids that have a high vapor pressure, usually have very weak intermolecular forces. And that maintains that relationship, that the higher the vapor pressure, the weaker the intermolecular forces. Ionic compounds have very low vapor pressures. That should make sense because the ionic bond is much stronger than intermolecular forces. There are strong Coulombic interactions, and so vapor pressure actually decreases as the intermolecular force increases. And since ionic bonds are very strong, ionic compounds have very low vapor pressures. Covalent network solids are always composed of nonmetals, one or two nonmetals held together by networks of covalent bonds. And often it's a carbon group. So the biggest examples of covalent network solids, if you guys remember when you did that one virtual lab, a diamond, not that we had that, but we did have graphite. So those are two carbon compounds. Covalent network solids often have very high melting points, and they're normally very hard. The atoms are covalently bonded. They have fixed bond angles, and so it's going to take a lot of energy to disrupt this. And so graphite, basically the carbon atoms form a two-dimensional network solid, has trigonal planar geometry around every carbon atom, and in a network solid, each sheet is considered to be one molecule. Here, each carbon is going to have a lone electron, so the electrons are free to move around. So graphite can actually conduct electricity. This is kind of how your pencil works. So these sheets are sort of free to slide over each other. And when you write with your pencil, layers of carbon actually slide off, and that's what's deposited on your paper. Kind of cool. Okay. Carbon's fourth valence electron, it's the one that's not in a sigma bond with another carbon, finds itself between the sheets. And so you have some pi bonds. Weak pi bonds and London dispersion forces are going to allow the sheets to slide over each other. Silicon dioxide is the empirical formula for quartz. And if you think about the strength of quartz, it's actually very similar to a diamond. And so it's going to take a lot of energy to disrupt that structure. We talked in the previous lecture about the protein structure and the intermolecular forces that hold proteins together. So hydrogen bonds form between the oxygens and hydrogens that are bonded to nitrogens. And so we get a secondary structure of a protein. Tertiary structures then are going to be caused by intermolecular reactions. So if we heat a protein, we'll actually disrupt that tertiary structure. If you remember from biology, the overall shape is going to determine the function of our protein. And so there's an active site, and it's actually chemically controlled. So a groove creates the opportunity for a protein to interact with other molecules. And remember, enzymes are going to break down the other molecule So a little bit of biology review there for our proteins. If we have water-soluble proteins, that means our protein can dissolve in an aqueous environment. And back when we talked a little bit about the structure of the cell membrane, you'll remember that the protein could, that the cell membrane could be so that the hydrophobic or afraid of water part was on the inside of the structure of the protein, and that the water loving part was on the outside. And that actually helps us make the membrane for our cells and stuff like that. So kind of cool. And so just a little bit on protein structure to put in that biochemical aspect of along with chemistry. All right. Some synthetic polymers. These chains, plastics are nonpolar, so they're only held together by London dispersion forces. And these chains can be thousands of carbons long. So some of the properties of synthetic polymers, they're generally flexible solids because they have London dispersion forces. The carbon chains can slide over each other because those dispersion forces are weak. And so plastics, because of that, can be stretched, especially after they've been heated. Metallic solvents, bonding is not covalent. There's not enough electrons to fill octets. But the bonding results from attractions between nuclei and delocalized valence electrons. So if you look at sodium, sodium has one valence electron. So the bond strength, in the case of metallic solids, the bond strength is going to increase as you increase the number of bonding electrons, okay? And so if you look at the electron configuration for iron, you have argon, and then 4s2, 3d6. So to figure out, and here we have neon, 3s1. So our sodium has one valence electron, or one electron, one bonding electron, so to speak. Our bonding electrons are any of these that appear after the electron, the abbreviated electron configuration. So it's these 2 4s's as well as these 6 3ds. And so there are more electrons. And so the iron, the metallic bonds in iron will be stronger, harder to get into from a solid to a liquid phase. And so you'll notice the melting point much, much higher, more energy is necessary. So the electron C model accounts for the properties of metals. And we studied this in a previous unit. The free movement of electrons allows the metals to conduct electricity. And this electron movement also allows metals to conduct heat rapidly. So if you heat one end of a metal bar, you'll actually transfer heat to the electrons in that area. And then those energized electrons will move to the other end of the bar, carrying the heat with them. There are no directional bonds like we saw in ionic solids, and so metals tend to bend but not break when you hit them with a hammer. So you can apply this model to both pure metals or our friend, the alloys. And just to review, we have an interstitial alloy, and we can identify them because interstitial means between the spaces. So carbon is going to fill some of the spaces between the iron atoms. Interstitial carbon atoms make the lattice more rigid, and then that is differentiated from that in a substitutional alloy. This is brass, and notice these molecules are about the same size. So that's kind of a review of something that we have studied previously. So that should do it for our notes on the properties of solids, but as always, if you have any questions, feel free to let me know. Thanks, guys.